hope you all had a good morning, and it's turning out to be a wonderful afternoon. Uh, I want to officially welcome you to the presentation, which I hope won't take a lot of time. For those who don't know me, my name is Mohammed. I am a full stack engineer, currently based in Mombasa. So I've had a few runnings with a lot of tools, front-end tools, back-end tools, and Docker, to be specific, is one of the tools that I cannot say I heavily use, but I sometimes use it for different purposes. So basically, we would like to start with a brief introduction into Docker, as in what is Docker. So the official definition is that Docker is a PAS. It's a set of tools that use OS level virtualization to deliver software in packages called containers. So basically, the main aim of Docker is to use OS level virtualization. And by OS level virtualization, it means that the virtualization is not at hardware, at hardware level. It's at software level, specifically the operating system. So the other parts are abstracted away, but the operating system kernel, basically Docker runs on Linux. Yes, you can run it on other platforms, Windows, Mac, but basically it runs on Linux. So you are able to share that Linux kernel uh, amongst a couple of containers. So basically, containers are just isolated Linux processes. It's not even complicated. A container is, uh, we'll get to that, to defining a container shortly. Let me not rush there. So most of the time people will say I'm using Docker as if it's just one tool, but basically Docker is a collection of tools. It's not just one tool. You have a lot of tools working together that basically form the Docker platform. So you have what you will install on your machine. You'll have the Docker server and the Docker client. Then we have registries where you can store those images. For example, Docker Hub. Docker Hub is like one of the most famous Docker registries. You also have some of these big providers, cloud providers, they have their own private registries. For example, Google has GCR.io. Um, AWS, I believe they have ECR, which is Elastic Container Registry. I believe something along those lines. Then there's also K.io, which is also a very popular Docker registry. So yes, we have a couple of those. And then we have other toolings such as Docker Compose, which allows you to quickly spin off a couple of containers that work together. Docker Swarm is also another tool which is centered around Docker. And there are so many tools that basically make up the Docker platform. So most of the time people will always refer to Docker like it's one single tool, but it's mostly a misnomer. It's basically a collection of tools. So most of the libraries are written in Go. Uh, it feels like for containerization stuff, it's like Go is the language of choice. There's some other tools that are written in other languages, other low-level languages such as C++, but Go is very dominant in these Docker tools. And it was released as an open source project way back in 2013. So let's look at other definitions of containers and images. An image is basically a file that bundles everything that you need to run a particular program. So let's say you have dependencies, you have libraries, you have the source code uh, that is required for you to run a particular application. So basically you take all of those assets, you bundle them into one file, and then you can use that file to run that particular application or that particular program that you're writing. So a Docker image is basically a file system snapshot, because those commands that you run to build a Docker image, they add onto that image layers and layers of uh, directories and files, depending on what instruction you've run. Basically, they stack up layer after layer, forming a snapshot of uh, of a file system. Further, a container is an instance of an image. So when you create an image, you will have basically you will have an entry point or a command that will be executed when you run that image to form a container. So basically, you will take that image and use Docker to run that image so that you get a container. So basically, a container is created from that image, which is a snapshot of a file system. So you will take that file system plus a particular command that is used to run within the source code that is within that file system to get an image, which is an instance of a running application. One thing to note is that a container is an isolated process. So basically, containers are actually black boxes. By default, they do not communicate with other containers unless you explicitly allow or instruct a container to communicate with other containers. And also, containers are very lightweight. If there's this cliche comparison of containers and virtual machines, if you look at it, the difference is virtualization in containers is at the operating system level, and then virtualization for virtual machines is at infrastructure level, at hardware level. So basically, in the traditional way of running virtual machines, you'll have one giant computer, and then you boot smaller virtual machines that feature an operating system. And because virtual machines need to have a whole operating system installed, they are very heavy because operating systems are enormous applications. Uh, so basically, virtual machines are very heavy. They take longer to start because you have to load all the modules, the software modules included in an operating system. But for containers, because the operating system is already running, the only thing that you need to boot is a process that shares that Linux kernel. So you can boot up a container in milliseconds. So they are lightweight, they use fewer computational resources, and they boot up fast compared to their virtual machine way of virtualization. So why would you want to use Docker? Uh, what is the rationale behind using Docker? The fundamental point behind this question is that Docker was designed to make it easier to create, run, and deploy applications using software containers. That's it. All the others are it's like benefits that you get by using Docker, but the fundamental um, reason why Docker was created was just to make it easier to create, run, and deploy applications in software containers. So if you look at the normal way, let's call it the normal way of running a particular program, you will get an installer for that program, maybe download it from the internet, and then extract or install it on your machine. Then you'll have those software binaries available within the file system of your machine. Then you can click on an executable or run a command script, a command line script to be able to run that application. That is the default way of running of installing applications. But with Docker, everything has been bundled into an image, which is a file system snapshot. You can just pull that image and run it. So it doesn't necessarily mean you have to install that software on your machine. You can quickly run that particular software even without installing it on your machine. One other thing is that containers are very portable packages, regardless of system configuration. As long as it's running Linux, whether it's installed on that machine or it's a virtual machine running Linux, you can bring in a container and run it, because regardless of what configuration you're running, the Linux kernel is what is important for running Docker containers. One other thing is that so many software packages out there have been containerized. Chances are, if you Google for a particular Docker image for a particular application, chances are you will find a ready solution for that particular software. And if you do not, you can always build your own, because at the end of the day, an image is a file system snapshot. So as long as you have those instructions for you to come up with that software package, you can always build your own. Uh, One other thing, we just said that containers are lightweight, they are quick to boot, they use, as far as resource consumption is concerned, they have a very small footprint, which means that they give you better flexibility, as you can have multiple containers running on the same computer, which might not necessarily be the case uh, with applications that have a larger footprint, such as an operating system. Uh, High availability computation is made possible because of the low overhead of starting a container. Containers take seconds to boot. So basically, there are scenarios where you want to make sure that maybe whenever a user signs into your application, um, that request can be handled. So you can have so many containers running, so that you make sure that those requests are handled concurrently and fast. And then when the load, maybe you don't have a lot of load, the users, the number of users goes down, you can kill those containers, and then you can spin them up on demand, depending on the amount of load that you have. So containers, they make some of these concepts possible because of the various advantages they bring onto the table. So the other side of the coins, there's nothing that features advantages only. Usually, there's another tail of disadvantages. So containers are still subject to performance overhead. Yes, they take milliseconds to boot, but those milliseconds are overhead. There's a latency between when that container starts and when your application is ready to receive requests. For example, if it's a web application, you have to give it a little bit of time for that application to boot, then it can start serving requests. So as much as it's fast, as much as they use very little resources, they are still subject to performance overhead, because the container has to communicate with the base operating system. So there's usually latency because of that exchange of information. One other thing is that Docker is open source. The core packages in Docker are open source, but some containers do not run with other platforms. Just like we've been talking, Windows is a very problematic platform to run Docker containers. So basically, you have to run like a virtual machine, a Linux virtual machine on top of Windows. Then you can run your containers onto that platform. So basically, because Docker primarily runs on Linux, it has those issues with other competing companies such as Microsoft. Containers are ephemeral. So basically, containers, uh, you can spin up a container very fast. You can kill a container very fast. As much as that is somehow an advantage, it's also a disadvantage, because they do not persist the state of that application that is running inside that container, unless you come up with solutions such as Docker volumes, for example. So let's say you're running a database application inside a container. Basically, the database application will require that there is persistent storage available, maybe on the host operating on the host machine, to be able to store the data for that particular application. If you do not map persistent storage and attach it to a container, when that container stops, all your data is lost. So yes, there are solutions that have come up, Docker volumes, to attach persistent storage to containers, but it's still not a very smooth process. There are a lot of caveats that you will encounter when you are doing the volumes thing. So it's far from a very smooth process. So maybe somewhere down the line, we'll have very robust solutions for handling the ephemeral nature of containers. But as at now, uh, it's still not a very straightforward process. One more thing is that Docker was primarily designed to be a solution for deploying server-side applications. So these are applications that you basically access using an API, for example, or you access using web services. But for applications that require a graphic user interface, like a graphic user interface tied to that particular application, it becomes very difficult to host that kind of application. Yes, there are software solutions that are looking to counter this kind of problem, so that you might be able to um, host graphical user interfaces with Docker, but they are far from robust. They are far from smooth. We still have a lot of glitches running those kinds of softwares with Docker. And then finally, microservices applications are the kind of platforms, or are the kind of scenarios where you will have you will reap the most benefits of using Docker as your platform of choice. For other runnings like standalone applications, the only benefit you get is a very robust way of packaging that application and deploying it. But most of the advantages of Docker manifest in microservice architectures. So I think we can quickly do a demo running a Docker container. I will try to make it as quick as possible. But before we get into the demo, maybe if we have a few questions that someone might want addressed, or maybe a quick question, we can present it before we go ahead and do the quick demonstration on running containers. Anyone? Any questions?
Seems none right now.
Okay. So I think maybe we can try to uh-huh. Let's see. Uh, just running a basic container, because I wanted us to have like a quick demo, not something very complicated. So we're just going to run an Nginx container, which is like a quick way of running uh, like a basic website. So basically, let's see. Let me see what images I currently have. Sudo docker images. Yes. So it seems we have an Nginx image that I have already downloaded. So at least it's going to save us the trouble of having to pull the image. So maybe we can quickly run it. Um, can we clear this? Uh-huh. So basically, running an image is as easy as using the run command. But there are a few important flags that you might want to use with the run command to control the behavior of that application that is going to be run. So usually I like to do my port mapping when I'm running that container. So basically, we are telling Docker to map port 80 inside the container to port 80 on the current machine, so that whatever is being served, or whatever is listening, so that we can reach whatever is listening at port 80 um, inside the container. So if I run this, we should have Nginx running. Yes, so Nginx is running. So if we opened a browser and went to localhost, just localhost, because we mapped port 80, we should be able to see a quick welcome page. So this is basically the default index.html that comes with the Nginx image. So running an image is as easy as that, but there are a few flags that we might want to check out. For example, dash p for port mapping, that one we've already done. Dash d runs your container in detached mode. That way, you will not see, if you use the dash d flag, you don't really see these logs. This is running in the foreground. So it's like the logs for that particular container are being pushed to my current terminal session. So if we were to do dash d, it will just tell us that the image is running, but the container is running, but we will not be seeing the logs as they are churned out by Nginx. Um, dash dash name. This is very important if you will later on want to, if you will want to interact with that particular container. So if I was to open another terminal and tell Docker to tell me what containers are running, let me just quickly make this larger. So huh, if we ask Docker to tell us to show a list of the currently running containers, you will see that there's a very like a random name that is assigned to the container that you are running. So if you wanted to control the name of this particular container, you can use the dash dash name flag to be able to specify a name, so that later on, if you want to refer to that container, you can quickly refer to it. Dash dash rm is basically to remove that container once it stops. So when a container is running, if you had run it using this particular flag, if you exit that process, the container will be deleted. So Docker PS for checking what containers are running is the current just the command that we run. There's another variation where you can ask it for all running containers. It will show you even the containers that have exited. So PS will only show you the running containers. Dash A basically will show you all the containers that you've run and you've not removed from history. So basically, you'll see that I some time back I ran a MongoDB database from a container. I also have PostGIS running as a container. I also have Redis running as a container. So whenever I need this particular software to run, I can quickly start it. And if you look at the way I ran these containers, I gave them, I used the dash dash name flag to give them a very friendly name. So for example, if I wanted to start Redis, for example, I'll just say, uh, because I gave it that particular name. So it will quickly start, instead of having to start copy pasting this random name that has been given here. I can quickly use the name that the custom name that I gave when I was running this container. So yes, Docker stats, we can look at the statistics for the running containers, see what kind of the resource utilization of those particular containers. So if we were to say sudo docker stats, Docker should be able to to give us a list of all the containers that are currently running, and show us the resource utilization of those containers. So right now, the Nginx container is, as you can see, it's based on an Alpine flavor. So the resource utilization is very low. And this is what we were talking about initially when we were looking at the advantages of Docker, that it has a very small footprint. Okay, it depends on what application you are running and what packages are installed. But for now, if you look at this, it's barely using the CPU, and it's only using a very small percentage of the RAM. So I won't even feel a pinch running this particular image on my machine. Uh, one other thing that we can look at is the logs for that particular container. So if we were to copy the container ID and say and paste that particular, we should be able to see the logs that the last few lines that came from that particular container. And another variation of this command is you can use the -f flag to follow those logs. So basically, it will not just terminate that particular process. So if you were to go back to that application and maybe refresh, because we now have another access log, you will see that there's another log that has come out. So this is basically to follow or to show the logs as they come from that particular container. So yes, this is as like a quick introduction or like a quick overview of how you can run a Docker container. Basically, you will use the run command to run with a particular image for you to be able to initialize that image into a running container. There are a couple of flags that you might want to use with that run command to modify or to customize the behavior of that particular application that is running. You can look at you can quickly check what containers are currently running. You can look at the statistics and resource usage of those particular containers, and you can also look at the logs for those particular containers that are running. So that's basically what I wanted to share as far as running a Docker container, like a quick overview on how you can run a Docker container. If there are any questions, we can address them now, or we can go ahead to the next section. So the next demo is about interacting with a container. So basically, like we said initially, a container is a running process. Is an isolated Linux process. So basically, for you to interact with a container, is the same way that you would interact with any Linux process. For example, if we are running a terminal like this, for example, a Linux terminal, basically there's that program in the background that is running, that is attached to this particular session. So, for example, in Linux, this is a bash terminal. So there's that program that is running. So basically, we would communicate to a running process, a Linux process in three ways. Number one, we have the standard in channel, which basically listens for the user input. We have standard out, uh, which gives feedback from that particular process. So, for example, the logs that we saw in the earlier example, those are that is communication from the standard out channel of that particular Linux process. Then we have standard error, which is similar to standard out, but it basically gives you the error messages coming from that particular process. So basically, you should just treat a running container as a running Linux process. The way you will communicate to any Linux process is the same way you would communicate to to a running container. So we have the exec command, which comes from Docker, which will allow you to execute commands within a particular container. So I think I had an Ubuntu based, or rather a Debian based image. Let's see, so look at images. Yes, we have a Python 3.8 image. this is basically based off Debian, which means we have access to the bash terminal that comes installed with this particular image. So the command for interacting with a container is the exec command. Now, the exec command only works with running containers. If you want to execute a particular program using an image, or initialize a container and then run and then execute a particular program, you will have to use a variation of the run command. So, for example, in this case, our Nginx container is still running. So if we wanted to execute, let's say, for example, if we wanted to open a shell inside that running Nginx container, we can quickly say, let's quickly see what's the ID on our running Nginx. So we can quickly copy this ID, and then we can execute. And now, because this is Nginx Alpine, so we can use sh, because the terminal program that comes with Alpine is sh. Okay, we did not get that. Let's see. Interesting. Let's try using the run command. Let's see if we can get a shell running. I'm still not getting a shell. There must be an issue that is happening that I can't quickly see right now. Maybe I will remember what I was doing wrong, then we can look at that. But basically, we should be able to open a shell inside, or we could try another command.
-it.
Okay, we could. Let's try. I'm still not getting a command, a shell. I'll see what command I'm supposed to run for Alpine-based images, or maybe when the guys that were compiling the official Nginx Alpine image, they did not install that particular terminal. Program. So I remember I had an Alpine image. Yes, I have an Alpine image. So we can say, this should be able to give us, okay, I'm still not getting a shell. I'll see what I'll just quickly look at this, see what I'm doing wrong. But for some reason, I'm supposed to get a shell if I run the docker exec command on any running container. The demo gods are not with me today. So yes, to run a shell inside a running container, you just use the docker exec command, and then the container ID and the shell program that you want to run. So basically, you could, for Debian-based images that come with bash installed, you will just use the bash command to run, to be able to open a bash shell inside of that running container. I don't know, any questions, or maybe any additions, if maybe somebody saw what I was doing wrong, so that resulting in the inability to open a shell. Brian, did you say anything wrong that I did that I could not get a shell into that?
Yeah, I'm not sure. I usually add the interact mode,
I think
dash
maybe
IT. Should it work? If you put after exec, you put the -it.
Oh, so that we make it into interactive mode.
Yeah.
Yeah. Okay. By the way, let's see. let's try SH, and then let's make it interactive and TTY mode. Yeah, that was the thing. We had to run it in interactive mode. Sorry about that, guys. That was a quick overlook on my side. So basically, the exec command running it interactive mode, it should open. So the exec command will basically execute that shell program and exit immediately. But if you specify -I, which is interactive mode, now it will allow you to interact with that particular program. So this is why you can see that we now have an open shell, and we can run any basic Linux commands here. So you can see where you are on 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 the file system, on the Linux file system that is running on that particular container, and you can use the normal commands that you will use in any Linux operating system to be able to interact with the programs or run any programs within that particular shell. So thanks for that tip, Mr. Brian. Very much appreciated. So we can just exit this, and we should be able to exit that shell. Yes, so we can run a shell in any running container, or we can run we can run an image to get a container, and then run that particular shell within that particular container. So yes, I think we can move on to the next section, which is basically building an image. So basically, building an image is a step-by-step process where you specify instructions on how you want to build a particular image. So basically, you use a Docker file. A Docker file is an imperative way of telling the Docker daemon, which is like the process that is used to build the Docker builder that builds that particular image. You are giving it instructions on exactly how or what steps to take so that the end product is the particular image that you want to build. So the common steps that usually you will do is basically choosing a suitable base image. uh, you will install system dependencies or maybe system updates should you need to do that, and then you will install libraries and the project dependencies, for example, and then you will copy the source code that you've just written into that particular image. If any ports should be opened, you will open those particular ports and then specify the initialization command. So like we said initially that whenever you want to run, you want to start a container. A container is an instance of an image. So you will take an image uh, and use a particular initialization command on that image to get a running container. So basically, by default, you should always include a default initialization container, so that if somebody just runs a particular image, they can quickly get a running container out of that image. So there are scenarios when you would want the person to run an image and also specify a command. Basically, if there was a default command for that particular image, it will be overwritten, and the one that has been specified will take precedence. So let's look at a very quick way of building an image. Uh, I believe I had a small project set up. Let's see. Let's look at Docker test. Okay. So if I can quickly take you through this more, can you see my IDE?
Definitely, it's okay.
Okay. I just don't want to be talking about stuff and maybe you're seeing something else. So basically, this is a very small. It's not even. This is a hello world example of a fast API application. It's as simple as they can get. So basically, you just create an app and define a route. Um, I installed the dependencies in a virtual environment, and then using pip freeze, I um, I created the requirements file uh, for the requirement for the packages that have been installed in that virtual environment. So if we can quickly run this, okay, the windows are becoming too many now. Yeah, let's see. Let me quickly activate this virtual environment. So if you've had an opportunity to look at the fast API docs, the way you would quickly run a fast API application is using the UVCon ASCII server. So you'll quickly say up, up, dash, dash. That is the quick command for running a fast API application. And if we can visit this endpoint, you will see that we have a running application on localhost running our Hello World application. So basically, the API is running. As simple as it is, it is running. So let's quickly shift gears to checking out how we can create a Docker image using a Docker file. So this is a very simple example of a Docker file. So basically, the steps that we had covered earlier, or the steps that we talked about earlier, you will want to choose a base image, set a working directory, and then copy the code. For this example, you see that we are not doing any updates. But if, for example, we wanted to do operating system updates, we could maybe say run uh, update. For example, because I know Python 3.8 Slim Buster, this is an image that is based on Debian Buster. The Linux flavor is Debian Buster. So I know Debian, the package manager is the apt package manager. So I can quickly run that command and be able to install the operating system updates. So next, you basically copy the requirements file, then install those libraries, and then next we are copying the source code for our particular application, and then after that we are exposing the port that we want this application to run on, and then the entry point is the default command that will be used to initialize this image to produce a running container. So we initially say that a Docker file is a step-by-step declaration of how we want the Docker builder to build our particular image. So this is the outline of the steps that we will want to use in order to build our API into a Docker image. So if I was to quickly run a build for this image, I would say I will stop the running server I will stop the running server and make sure that I am inside uh, that folder with the Docker file, and then say sudo docker build. So basically, the build command is what is used um, in conjunction with a Docker file to be able to build an image out of the source code that you've written. So in this scenario, we're just telling the builder that look inside the current directory. You will see a Docker file. Use the steps outlined in that Docker file to build an image. So basically, we are telling the builder to build that, and you will see it going through the instructions as we the instructions as we actually specified inside that particular Docker file. So you'll see that it's bringing in the base image, and then it's switching to a working directory. It copies the requirements file, and the reason why this went very fast is because I had initially built this image, so that's why it went really fast. But if I was to change any particular any part of the source code, it would go back to be able to build uh, that particular image from scratch. So it also copies the source code, exposes the port that we want, and then sets the entry point for that particular image. So right now we have this image that has been built, and if we were to run this, we just say sudo docker run that, and we should be able to see our API running in a Docker container. So basically, that is what you would want to do if you wanted to build or let's say Dockerize your particular application, the application that you've built. It's all about identifying the steps that you will go through, from choosing a base image, installing operating system dependencies, installing project dependencies, and then copying your source code, opening any ports should the need should you need to open any ports, and then specify the default command for running that particular application. So now you can see that we have our API running inside a Docker container. Okay, it doesn't want to stop. Interesting. So I think that's it for that particular demonstration. I didn't want us to go into very advanced ways of building images, but something that is of interest to me, I really like the way it works, is multi-stage builds. So should anyone be interested in looking at that? That is a very interesting topic as far as building Docker images is concerned. Doing multi-stage builds, which helps in making the build process much more robust. It also helps in trimming down the image sizes. For example, if you were to look at this scenario, let's quickly open another. So if we were to look at the images that are currently on my system, we'll see that the latest one that we built is 264 megabytes of size. And if you look at the base image, which is uh, Python 3.8 Slim, this one is 114. This one is 114 megabytes. So the difference between 114 and 264 is basically what the source code that we copied into that image, the dependencies that we installed. Actually, the extra is what is what is accounted for by those steps that we've done, because basically Docker will build an image layer after layer, and each instruction corresponds to an additional layer built on top of that image, uh, towards getting the final output, which is the final image that you want to build. So you will notice that our image currently is 264 megabytes, but if we were to maybe do a little bit optimization, we should be able to slim this down maybe to 200 megabytes or something around those along those lines. So that is what I wanted us to do as far as building Docker images is concerned. I think we can go to the next section, which is Docker in geospatial applications. So, in considering Docker, there's this cliche saying that spatial is special, but when it comes to Docker, spatial is not really special, because uh, the way you Dockerize other applications or the way you package other applications with containers is the same way you can package geospatial applications or geospatial um, services using Docker. So if you were to go online and search for any geospatial software or application that you would want to run in a Docker container, chances are you will find that containers are available for that particular application. For example, if you look at PostGIS, I most of geospatial analysts, geospatial engineers, at one point in time, you will have run-ins with PostGIS. So this is the image that I currently use, and this is not the only one. I'm sure there are other flavors of PostGIS running in containers out there. And if you feel that the current ones they do not meet your needs, you can always do it yourself and build your own images by following the steps that you would want to follow to build that particular image. So GrassGIS, GeoNode, I think Brian has a lot of experience with running GeoNode in a containerized environment. GeoServer, we have a couple of images out there that you can use to run GeoServer in a um, containerized fashion. PostGIS, as you've seen, Force. For our guys, Rocker Geospatial has some very interesting images for running our applications, our geospatial applications using Docker. So if anyone is interested, I know in our group people are interested in R, so they can quickly check that out and they should be able to get. Yes, I can see someone raise the hand. Hello?
Davins, you can speak up.
Hi, Mohammed.
Hey.
I think the list is never ending.
Yeah, the list is, that's why you see the last item on the list is etc. Because
I was just curious about the bit where you're writing, where you've written indicated force. I think that's a new one to me.
Yeah, Brian is more. It's also a new one to me, but Brian has had runnings with this. Maybe Brian, if you can quickly elaborate on this on this platform.
Yeah, sure. I can actually explain it a little bit. So, FOSS was created mostly for guys interested in remote sensing, right? And it's basically also under the principle of building analysis ready data, like assuming you want a data set that's cloud free and all the remote sensing capabilities of cloud of data processing has been done, including things like, which was interesting again, they also have like this topographical correction where, for example, they remove the shadows from the valleys and such kind of stuff. So it's an interesting stuff. You can really check it out. I think I can share. I'll share the link on the chat. Yeah, so it's just an interesting, and yeah, it's Dockerized, so it needs someone to have knowledge of Docker definitely. Then you can easily set it up and use it without installing any software, which is really great. Yeah.
Okay, thank you.
Yeah.
So yes, and I see that there's a link in the slides.
Oh yeah, actually you can click the
yeah.
link. Yeah, you can click to read the docs there kindly. So the link doesn't want to open.
Just
it's acting up. It's showing some.
Yeah, so the thing is that the tons of technologies out there. Yeah, so that's FOSS framework for it's actually an abbreviation for operational geometric correction for environmental monitoring. Yeah, but it does a lot of things. Yeah, and just you can see it has capabilities to process Landsat, Land 7, Landsat 8, Landsat 2. And yeah, it's just the main goal is just to make you focus on analysis, but it will do the processing, all the processing for you to make it analysis ready, right? And that's the goal.
Yeah, so basically, like we've said earlier, with Docker, the list is endless. I mean, almost everything these days has
Yeah,
an associated Docker container that you can use to run it in a Dockerized environment. So, and if you do not find a ready one, or if the ones that are out there do not meet your specific or your requirements, you can always build your own, because Docker is actually very interesting as far as getting your hands dirty and doing a couple of things and tweaking and tinkering with images is concerned. It's really interesting.
yeah, Mohammed, maybe what you are not shown is maybe the Docker Hub, because maybe people who are hearing about it for the first time might not be aware where to get these images from, or even to get the base images and stuff.
Okay, so
Yeah,
yeah. So I think what I can do is I can quickly so basically, if you run an image, for example, if you run an image, what Docker will do is it will look in your local cache. It will search for the image in your local cache and see if it's available. If it's not, it will tell you that this particular image is not available. So it will go online to Docker Hub to fetch that particular image. So for example, if I was to run, let's just run Nginx, the latest version, which is based of Ubuntu Debian. So Docker will basically say that it's unable to find that image locally. So it will go online and pull it from Docker Hub, which is the default registry for Docker. So basically, we have a lot of let's see, Docker Hub. Okay, is my internet starting to act up? So yes, you can search for any image that you want to use. So basically, they are the official images that are maintained by Docker, which are like for example, the Nginx image that we were using, the Python 3.8, that is also an official image. But there are also other images that have been created by other users. So for example, if we are to search Nginx, we should be able to see a couple of images that are related to the Nginx project. So you will see that this is the official build, and then you will see this is Ingress Nginx built by Nginx, the company. And then, yeah, so you'll see that Nginx demos, so many people have created images that are based off Nginx. So if you feel that you want to use the official image, well and good. If you feel that somebody else has an image that you find interesting, you can always look at that. And also the good thing with Docker Hub is you can you have what we call tags. So basically you'll be able to see, for example, this is you have Nginx Alpine, which basically is based of Alpine. So you will see that Nginx Alpine is lighter compared to. Um, so let's quickly stop this one so that we can compare the sizes. So if you look at Nginx latest and Nginx Alpine, you will see that these are the two images. The Alpine image, because it's based of a smaller Linux distro, Alpine, we know that the base distro is around 5 megabytes in size. You'll see that the Nginx Alpine flavor is smaller if you compare it to Nginx latest, which is based of Debian. Yeah. So the mainstream Nginx is based on Debian, and Debian being a heavier operating system, or being a heavier distro than Alpine, you'll see that both images will run an Nginx application, but the difference is the base operating system that they are built upon. So you'll see that Nginx latest based on Debian is heavier than the one based on Alpine. But there are scenarios where you would want to run Nginx that is based on Debian. Maybe you have some specific packages that you want to use, and they're available in Debian, and they are not available in Alpine, for example. So yes, you would want to run Nginx latest rather than run Nginx Alpine. But if you only want Nginx and you really don't care so much about what operating system is the base operating system, and you want to minimize the footprint for that application as much as possible, then you can always go for Nginx Alpine. And most of these images, in fact, if not all of them, they usually have an Alpine flavor, which is also about running a smaller application footprint. So if you look at this, you'll see that Nginx latest, which is 1.19.10, is based off Debian. But for those who want to use a smaller image, they can go for that same version, but based on the Alpine the Alpine Linux distro. And yeah, so depending on those particular functionality that you want from that image, you can even look at the architectures, the architectures that these images can support. So you can always build your own if you feel that the current available images do not satisfy your needs. But chances are you will always get an image out there that is ready, and it satisfies your use case. So we can also look at Python, because I know most of us here write Python code. Being geospatial guys, we always want to write Python code. So yeah, so this is the official Python, and based on the tags that or based on the versions that you want to use, you can see that we have all the way from Python 3.6, and basically you can have any Python version you want. So yeah, you will see that most of these, some of these are lighter than others. So basically, depending on the version that you want and the flavor that you want, you can always choose which tag you want to go for. So yeah, Docker Hub is the default registry for Docker. Most of us, if you build your own custom images, you will want to push them to Docker Hub. Or if you want to use other people's images, you can also find them on Docker Hub. If you want to use the official images, you can also find them on Docker Hub, which basically has a lot of images there. There's also k.io. Now that we were mentioning registries, which I find of late it's gained a lot of traction among developers who basically containerize their applications. So yes, k.io is also, it's also a very popular registry for storing your containers. Yeah, so you can pull images from k.io. You can upload your images by creating repositories. You just have to create an account and create repositories on k.io, and then you can push your images there. So some of these registries are if maybe you work in an organization where they store uh, their images on a particular platform, you might be forced to go to that platform. But by default, Docker is like the go-to registry as far as Docker containers are concerned. So yeah, I think I've covered some of the issues that you're talking about, Brian, regarding Docker registries. So it's all about exploring what other tools surround the Docker ecosystem. So I think you cannot mention Docker without mentioning Kubernetes, because it's one of those tools that have really gained traction with the advent of Linux containers, Docker, and other um, container platforms. So basically, Kubernetes has really gained traction over the last couple of years. It's a really interesting technology, uh, which is basically based on running containers, containerized applications. So yeah, Docker Swarm is also another one. Although maybe I can say Docker Swarm is not as popular as Kubernetes, but it's also there. There are organizations out there who use it. So it's also an interesting tool to look into. Yeah, so I think with that, we just have one more section to go, which is basically uh, just a short list of resources that can get you started with Docker. Um, there are so many resources out there. There's a billion, tons of resources out there for learning Docker. So for those who are interested, for those who for those who want to begin using Docker, for those who have some knowledge on Docker and they want to further the knowledge, there are so many Udemy courses out there. There are so many documents out there talking about using Docker in your workflows. So you can definitely check it out, and I'm sure you'll be able to get something to guide you along your journey as you tackle Docker as a packaging and deployment platform.
Yeah,
So I think maybe if we have any questions or any other discussions, we can uh, bring them up, because that brings me to the end of the presentation.
yeah, sure. It was an amazing one. I think yes, the Vince has added the mock.py. Was also great for the for learning and stuff. Yeah, so it's basically about learning. Yeah, Docker is getting traction. It's a great thing to have. It doesn't matter if we're into software engineering or that science. I think most will share the tools. And yeah, it's just up to you to dive. If you're not used to writing scripts, maybe you are used to Windows and the GUI. Yeah, it might involve some knowledge of Linux. Knowing about the Linux system a little bit, I think will come in handy. But apart from that, I think it's just an easy thing once you understand it and how it works. Yeah, the floor is open for any question.
So basically, Brian, you have access to this particular presentation, yeah? So I
Yeah,
think you can also make it available. I think I gave you all the necessary permissions to like
yeah,
share and do
sure,
everything
sure.
with this. Yeah, so maybe you can also share it with the other guys, so maybe
Yeah,
they
we'll
can look at it, and maybe we can even make it better if somebody maybe has something to add on to this
throw it on.
presentation.
Yeah,
Yeah, we can add on to it and see what we can do with it.
yeah, sure. Seems it's confusing. Betty, are you now satisfied or confused?
Sorry, Brian, come again.
I
Am
was
I?
asking, are you satisfied? Is it clear or it's confusing?
Yeah, I am. Thank you so much for the presentation, Moha. We've really learned
You're
a lot.
welcome.
And thank you, Brian, for organizing this and even the rest of the congregants. Thank you for joining in. Because our
Okay, great. Yeah, yeah, Docker is pretty strange, I think, for most Geo people, but yeah, it depends. Once you start using, or you'll realize there's a time you need it. Once you're doing some stuff, you'll always come to need it maybe later on, if not sooner.
But if you ask me, I'll say that even if you don't use it in production, it certainly makes some of these things easier, because I remember when I used to install all my databases on my machine.
Yeah,
So if maybe I wanted to do an application with maybe MongoDB, I would have to install it on my machine. I would always have PostGIS installed. I would always have Redis installed. Sometimes I would have RabbitMQ installed. And you feel that these things are all clogging your machine. You have a lot of background services running, and maybe you're not even using them at that time. So I figured it also makes some of these things easier, even in development. Yeah, because for example, for me right now, I strictly run all my databases as Dockerized applications. I don't have databases installed on my local machine. If I feel that I want to write an application with maybe PostGIS, I'll quickly spin PostGIS in a container and connect to it from the application. And yeah, that's it. So basically, what I usually do is I just map some volumes for persistent storage of the database data. Yeah, and that's it. You have made your development workflow easier. So basically, like we've said, the fundamental reason behind Docker is making development and deployment of applications easier by using containers, and it's really amazing how far Docker can go in simplifying your development experience, um, rather than having to install dependencies and all that kind of thing on your local machine.